Okay. So today I want to talk a little about what happens when you have singularities on the hypersurface. So let me first mention that singularities affect the birational geometry of they can affect the birational geometry. Consider, for instance, the case of a quartic 3-fold in P4. So this is one that is Koski-Meining theorem. So we know that if it's smooth, then it's super rigid. But suppose now that this one is not smooth, maybe it has a double point. So a point of multiplicity 2. So what happened here is that I can take a linear projection from the point. So X is contained in P4, and I can project down to P2 to P3, just a projection from the point P. So this map is a birational map on X. Now, so if you think about how do you study the degree of this map, you take a line, a general line through P. That will be give you a general fiber from P4 to P3, and they will intersect X in 4 points, but two intersection points actually are already in P. So there's only 2 additional points. So this is an involution, it's a 2-to-1 map. It's a birational map, but the degree of the map, if you like, the degree of function fields is 2. So it means that there is an involution here, which is only a birational involution. So tau is an element, a birational group of X, but it's not an automorphism of X. It's a birational involution. The one swapping the sheets of the cover. So in particular, it cannot be birational super rigid. And then, you know, this thing was studied by Kort and Mella. It was studied by Publico first. And under some conditions on the singularity, how many singularities are there, one can still prove some weaker version of rigidity. But this is just to give a motivation, just to so you're aware of the fact that singularities do affect the problem. So the theorem what we want to talk about today, and I put an asterisk here, just because about asterisks first. So, well, this theorem is motivated by the discussion we had in the course. So I will explain what the previous results on this, and I think that the technique can be adapted to get this result. But since it's fresh, maybe I put an asterisk just in case. So for every n greater than 6, then every hypersurface xn and pn, so degree n, with only ordinary double points as singularities. Birational super rigid. Okay, so first of all, Amy, what does it mean, ordinary double point? So this means that you look at a point inside X. It's an ordinary double point, which I will abbreviate with initials. It simply means that if you look at the tangent cone, this is a cone over a smooth quadric. So another way of saying is that if X is defined by some function x equal to 0 at P, locally at the point P, then the polynomial is going to start with squares from, let's say, the coordinates, plus some higher order term. And the tangent cone is precisely defined by the quadratic polynomial. So it's a the quadric of maximum rank. So maybe briefly, the case n equals to 6, this was studied by Chelsov. This is assuming there are no planes inside X. So there's a technical assumption. And then the case n greater than 20 follows. Actually, before that, let me actually. So, and then in the case when X is general in moduli. So you look at the space of the moduli space of hypersurface with the ordinary number of points, and then you put some genericity conditions, so some open sets there. Then this was done by Pupikov. And then the case n equal to 20 is followed by some result that I did. And now with this extent also you fill up the gaps in between and complete the case n equal to 6. The case n equal to 5, this remains open. At the moment, it's not clear whether it should be rigid, partially super rigid or not. It's plausible, but the method doesn't quite stretch to cover that case. Okay, so this will be an opportunity, first of all, to discuss the fact that when we define singularities of pairs and multiply ideals, so I assume everything goes smooth just because it simplifies the definitions a little bit. But in fact, you don't need that. So the definition can hold more generally. So let me just talk about that a little bit. So talk about log discrepancies. Over singular varieties. Okay, so suppose X is a normal variety. So normality is a common assumption. Of course, there are situations where you actually even need to relax that assumption. For instance, if you study moduli, just think about moduli of stable curves, you end up with nodal curves and certainly not normal. But for most of the theory, apart from that point of view, this normal variety is a natural assumption. And now you want to put the following condition. So you look at the canonical class, Kx, and you ask that this is Cartier, or at least Q Cartier. Q Cartier simply means that some positive multiple will become a Cartier divisor. So in a normal variety, you need to distinguish between a Weil divisors and Cartier divisors. So you could have a Weil divisor is not Cartier, but maybe twice the divisor become Cartier. So that's like a Q Cartier condition. Okay, if you have this, then you suppose say is some Q subscheme in X. Suppose E is a divisor over X, and let me also tell you where it lives on some resolution Y. Okay. And then we can define a dot discrepancy in the usual way. So the definition is exactly the same I wrote before. You look at the order of the discrepancy of the divisor over X. So this is the order of Ky over X. You add 1, that's where the word log comes in. And then you subtract the order along E or the Q subscheme. Just think about Z as a divisor or Q divisor or Q subscheme. So the key point here is, what is this guy? So Ky over X, again, is a unique exceptional divisor or exceptional Q divisor, which is linear equivalent to Ky minus the putback of Kx. And the key point here is that this guy is well defined. So this is where we use this assumption, B Cartier or at least Q Cartier, to define a putback. Okay, so in general, this could be a QKT divisor. If Kx is QKT, then the relative canonical divisor will be QKT. Because in order to pull back Kx, I need to take a multiple, pull it back as a KT divisor, and then divide. Okay. So, and then given this, so the definition, singularities, multiple radials. Extend in obvious way. And then you still have properties such as, for instance, the Nado vanishing theorem and inversion of adjunction. At least for KLT singularities, which is the statement that I actually gave. So there is a more general inversion of adjunction, which is open in full generality, but this one about KLT, which is in any case for something we're going to consider, we're going to put some additional condition on a singularity, which we're going to talk in a moment. So it hasn't really changed much. It's just the only delicate thing is that I need to be a little bit careful in the definition of the relative canonical divisor. So it's also sometimes useful to introduce some the following notation. I avoided it before, but just for the proof, I'm going to introduce the following notation. Again, this is a special case of a general notation. If I give a point P in X, I define the MLD at P of a pair XC to be the infimum of all discrepancies of the pair, where A is a divisor over X, the center in E is equal to the point P. So this is called the minimal law discrepancy.
Oh.
So you see, for instance, that if the minimal law discrepancies is negative, then the pair, it means that there is something with law discrepancy negative, and therefore the pair is not law canonical. And in fact, at P, and in fact, one can prove that there is if and only if. So there's another way of detecting law canonical thresholds and talking about singularities, keeping track of the discrepancies. So this dot discrepancy defined here, that is what is come naturally in a minimal model program. But there is not the only way to measure in singularities when X is singular. So I want to talk also about that. So there is also another way of measuring singularities when X itself is singular. Okay, so I want to define what is called the matter log discrepancy. Okay, so what you do is that you're going to define another discrepancy, which has the following notation. So you're going to use the same notation as before, then you're going to put a hat on top of the A. So the way you're going to do is that you're going to define the order along E, and instead of using the relative canonical divisor, you're going to use a Jacobian ideal of the map, and then the rest is the same. And then you subtract the contribution of coming from Z. Okay, so what is this thing here? Now this thing is something different now. So this is a Jacobian ideal of the map F. So by definition, this is defined by the appropriate minus of the Jacobian matrix of the map. So the map, you fix some coordinates locally on Y, fix some, so think about analytically, fix some coordinates, and you look at the equations Fi, and if I take a partial derivatives of the equation of the map. So this gives a Jacobian matrix, and then there's a correct size of minus you want to look at, and compute those minus to define an ideal. So that's a Jacobian ideal. The name matter comes because this information relates to a matter construction of a matter class of a singular variety, which uses a Nash block. But we'll not get into that more than this. So let me give some remarks here. So the first one is that we have an equality between the discrepancies, law discrepancies, along some divisor E. This holds if and only if X is smooth at a generic point. Of the center of E. So the point is that what I want to say here is that if I compare the relative canonical divisor here, this contribution came from the relative canonical divisor, and the contribution coming from the Jacobian, if X is smooth, X and Y are both smooth, then I mentioned this already, that the canonical divisor, relative canonical divisor, is precisely defined by the Jacobian of the map. There's an easy computation in local coordinates. But if X is singular, then the two things actually are different. And in fact, I can give you a precise formula in the following case. If X has local complete intersection singularities, e.g. an hypersurface, okay, then I can tell you what the difference is. So the matter discrepancy is always bigger for a singular variety, and in fact, the difference is the following. It's going to be the order along E with the Jacobian ideal of X. Okay, so what is this? This is Jacobian ideal of X. So suppose that X is defined by some set of equations, cutting out X and this. So when you look at the minus, appropriate minus of the corresponding Jacobian matrix. So now you take a derivative of the equations of X with respect to the coordinates in the ambient space. Okay. So you have two different Jacobians here in play. One is Jacobian of the resolution, the other one is Jacobian of the equations. And the difference is exactly what gives you the relative canonical divisor. These are things that are not hard, but they're not completely straightforward. I have included a proof in the notes if you're interested. It shows exactly this formula. So if you're interested, you can look at the proof in the notes. Any questions about this? Okay. So the next thing I want to talk about is something new in this course, a new way of bounding singularities. So this label this under singularities and via generic projection. Okay. So let me talk about this. So the proof of the theorem we split in two cases. Okay. So I will cover the high-dimensional cases precisely when the dimension of the ambient space is at least 9. For this, I will use a method similar to the proof in the smooth case. Okay, so I follow exactly the same strategy of computing some lengths of some multiplier ideals, and then I contrast it with some condition coming from Nether vanishing. Because of the singularities, if there are singularities, I lose some, I'm gonna have to cut down more, and I need to apply these inequalities on smaller dimensional spaces. We see this in the proof, and that gap is gonna make the argument only work for dimension, I guess, x dimension 8 and higher. So n greater than 9 instead of n greater than 5 that we had in the smooth case. So this leaves open a few log-dimensional cases. So for the lower dimensional cases, this is when 6 less bigger than n equal to 8. So this we're gonna consider some projections to a lower dimensional projective spaces. Again, I will explain more what that means. So this actually, this idea goes back to Publikov, and then was actually further developed in my paper, in a paper what with Ein and Mustafa, where we proved the smooth case in low dimension. So the strategy is very similar to the strategy in this paper here. Okay, so I'm gonna have to break the proof into these two pieces. So we already have everything set to discuss this part, but we need to make sense of this project, what it means by projections, and what kind of information I can get out of it. So this is what I want to discuss now. So let me consider the following setting. Suppose X inside N. So say for now is a smooth smooth variety, n-dimensional variety. Suppose inside here I have a Z to be a complete intersection closed of scheme. Of codimension K. And I suppose that E is the divisor over X. Okay. So what I'm going to do is that the idea is that I want to project down to a low dimensional space, keep projecting until I get something in codimension 1. So as Z has codimension K. So if I project down, for instance, to a fine space of dimension AK, AN, little n, then Z will still have dimension, codimension K. but then I keep projecting, then the dimension is going to drop down. If I take generic projection, so that the map on Z is finite, the dimension of Z remain the same, but the dimension of the space gets smaller up to the point where I get a divisor. So this is what I'm going to do. So I'm going to consider general linear projection. Phi. So I have X inside my finite space, and then I'm going to project down to some Y, which we're going to have some low dimensional finite space, to M, and I take M to be N minus K plus 1. So inside here, I have Z, which is a subscheme of codimension K. And what I get on this side, so how do you push forward a subscheme? So you have different options. You can take the scheme image. That's certainly a very valuable way of doing things. But I claim that that's not good. The reason is that if I just take the scheme image, I'm going to lose all the information I have along the fibers. So I want to keep track of that. So what you're going to do is that you're actually going to push forward as a cycle. So you push forward the cycle associated to Z. So now this is just a cycle, it's not a subscheme in general. But because I'm codimension 1 on a smooth variety, so this is a cycle of codimension 1, so I'm going to regard it as a Cartier divisor. Okay, so in a way, I can think of it as a subscheme. Because in codimension 1, it's the same thing. So this is what we do. So here's another fact that I'm not going to explain. This comes from valuation theory. So I look at the order along E. So I think about this as a valuation on the function field of X. I notice the function field of X has an inclusion for the function contains a copy of the function field of Y when I just get the pullback map. Every rational function Y, because it's a dominant map, we give a rational function of X. So I can restrict order E as a valuation to the function field of Y. And if I do that, I get a valuation. And in fact, I don't just get a random valuation. I just use a little bit of a theory from valuation theory. I get a valuation that looks just the same, almost. So it's going to be the valuation along some divisor F up to some rescaling, potentially. So there's some B here. So what is it? F is a divisor of a Y, and B is some positive integer. If you just think about geometrically, for instance, for a finite map, you take a diagram where you extract F and you look at, and you keep blowing up, and eventually you're going to be a finite map over there, and then E will cover some divisor F, and then some ramification index and so on. So B relates to the ramification index. Okay, so the theorem here now. The statement is a bit, takes a moment to absorb, but let me just give you two statements. Actually, let me give you the other way around. So if I take C to be the local threshold of XZ, then I can estimate the local threshold downstairs. I see the local threshold on Y. Remember, I put it forward from X to Y of this divisor. And I claim that this is going to be at most C to the K over k to the k. Remember that k is a codimension. So remember that I gave you an interpretation of local reconstruction of smooth varieties by an integrability condition. So you can think about this statement, and this actually was suggested by Su, that this is just integration along the fibers. Okay, just a way of thinking about what the statement says. More generally, for every C such that the discrepancy, low discrepancy, is non-negative, we have a comparison of log discrepancies. The log discrepancy downstairs, this new pair, but the coefficient now I'm going to put is the C to the K over K to the K times this value. And maybe I need to multiply by this rescaling. It's bounded above by the log discrepancy upstairs. Okay, so the second formula is a bit more complicated to simulate. I think maybe the formula on local reconstruction is simpler. And in fact, the way it was used in the first place. But today I'm going to use also the second case. So for instance, one can deduce from this a similar inequality on canonical thresholds. So the way you want to say, again, the way you want to think about this is don't worry too much about this, the precise formula, but I have a projection from x to y. I have a pair on x, z, which has some certain singularities depending on how singular z is. As z is a scheme of high codimension. And I push it forward until I land into something where z becomes a divisor, and I do this push forward, and that's where the integration along the fibers really occurs. Because I'm absorbing whatever is on the fiber in the coefficient of this push forward. And then I estimate the singularity downstairs. And this statement, it says that the singularity downstairs are very bad. They give you a lower bound to the singularities. An upper bound to local threshold is a lower bound on singularities. So this may sound something like completely new, but I'm claiming that in fact, you already seen this theorem almost, at least. So let me explain this as an example. Okay, so assume Z is a scheme of dimension 0, i.e. the codimension is the same as the dimension of the ambient variety. Okay, so in this case, where are we projecting? So I say the support of Z is just a single point. So I have X here, and now I'm projecting down to Y. So what is Y? Y in this case is just a 1. So I have a point P, and I look at the image of the point P, I'm going to call it Q. And I have a smooth vibration like that. Now here on P, around P, I have a big subscheme, which is Z. And what I'm going to do is that I look at it as a class in the Chow ring, in the Chow group, and I push it forward. So, and then this is going to give me something, a thickening. But now the thickening is only spread in one dimension. Before, the thickening was spread in n dimensions. But now, after push forward, it only spreads in one dimension. So this is the push forward of the class of Z. You suppose that Q, but it's a fat point also. So let's make the computation here, because here we can do the computation. So I'm going to write the class of Z. So how do you compute the class of a scheme? in this case, it's simple. It's just reduce at the support at the point. So you take as a variety is a point itself. And now I need to put a coefficient. So how you compute the coefficient? The coefficient is a multiplicity of z at the point. So it's the length of OZ. But this is the same because this complete intersection has the same multiplicity of the ideal of z inside X. Okay. And so the push forward of the class of Z is simply this multiple mu times the point Q. So now you think about this as a divisor on A1. So in particular, I see that the log canonical threshold on Y of this class, well, the log canonical threshold on smooth curves is a simple thing to compute. It's just 1 over the multiplicity. So it's 1 over mu. Okay. So in particular, I see that the sign multiplicity here, which is mu, did I do this right? Yeah, so it's the same thing as 1 over the log canonical threshold on Y, this thing. And this will be greater or equal, that is by the theorem. So let's look at the formula. I want to use this formula here. So of course, k is equal to n. So this will be n to the n over c to the n, which is, by the way, the same thing as n to the n over the log canonical threshold of xz to the n. So this is an equality between sign multiplicity and log canonical threshold that we proved before. So you can use this theorem as a generalization of the inequality between some multiplicity and log canonical threshold. And in fact, the proof uses generalization of that formula to fractional ideals. Okay, so we're going to use this. So the idea is that, again, keep this picture in mind. The idea is that we're going to have some high codimension. In fact, it's going to be a codimension 2 subscheme coming from the base locus of a rational map, partial map. And then we're just going to project down to the lower dimensional projective space and use this inequality to get conditional and singularities of the pair on the projective space. And then on a projective space, we have the tools we can use. Okay. So the last remark I want to make is that we also have a how about if X is singular? So here I'm assuming X is smooth, but you know that I'm gonna talk about singular hypersurfaces. So I'm gonna have to worry about singularities as well. So if X is singular, well, you have the same theorem, you just replace those discrepancies with matter. Log this. And that will do the trick. So the theorem, let me just state it here. Same assumption as in the previous theorem, except we allow X to be singular. Then we're going to have a bound on the discrepancy downstairs. It's going to be the same BAF, Y, and then there's this coefficient C to the K over K to the K times the push forward of Z. And that will be less or equal, and the matter law discrepancy along C. Okay. So if X is singular, then I cannot use a discrepancy and hope for the same result. I have to use a matter law discrepancy. Yes, is that a question?
Yeah, I have a question. I'm just a bit confused about this push forward of Chow groups. So is it not just the proper push forward that we're using here?
Yes. So okay, good question. So this kind of a bit annoying in the formulation, but yeah, I kind of been a little sloppy here. So what you do is that, because I want to talk about generic projections, just some general projection, that's kind of important. I mean, but really what you need, the one information you need here is that the map is finite on Z, okay? So what you can do is the following thing.
Sorry, it's finite on, sorry, what was that?
The restriction of phi to Z is a finite map. That's what the information you want.
Otherwise it doesn't make sense. Otherwise the push forward doesn't.
No, I mean, the push forward would kill the things that have dimensional, polydimensional fibers. So it still makes sense, but you don't want to do that. But then there's still, you want to work with proper maps. That's true. So what you do is you take a relative compactification of X over Y. So you reduce to work with proper morphisms. And now once you do that, then you can use intersection theory.
Okay.
Yeah. So that's in the proof, in fact, is that's what we do.
And then when you have the point upstairs, that was Z, like the device is pointed at P, we had this thickening mu, and then with the push forward should be something like the degree of the map times mu, right? Downstairs.
Well, you're talking about this particular example of a zero-dimensional scheme?
Yes.
So the degree of the map is 1, because you send 1 point to 1 point in this example. So I don't have that. The only thing I need to do is just to carry the coefficient, which is the multiplicity.
Yeah, okay.
And this is where, so this is exactly, this is an example to look at. This is exactly when you see this, what's used called the integration along the fibers. So you have the thickening of Z inside X in all directions. So this M is not just, if I just take the scheme image, I just get kind of a diameter, not get the volume, so to speak, if you follow what I'm saying.
Okay, yeah, right.
So, but instead, if I take the push forward of the cycle, I get all the thickening into account. So I'm also integrating all the fibers of the map from Z to Y.
Oh, now, okay, now well, the cycles makes more sense. Okay, because it's because of dimensional. Okay. Fine, thank you.
Yeah. Other questions? Okay. So again, these are kind of technical statements, but I hope that the example that we just discussed might actually be helpful to see what's going on. And the fact that, again, you want to think about this as being kind of a different way of thinking about the formal multiplicities that we discussed before. And in fact, the two statements, at least at the local and concentration, the two statements are essentially equivalent. Okay, so the next, now we can now move to the proof. So let's talk about birational rigidity. Or singular hypersurfaces. Okay, so there are results for other type of singularities in the literature. So, but here again, we only focus on. Again, I keep tracking these asterisks just in case. For n at least 6, if I look at hypersurface degree n in Pn with order and double point, is birational and superrigid. Okay. So a couple of remarks, first of all. So the first thing you should complain about is that when I define what birational or superrigid means, and I look at these maps to Mori fiber spaces and so on, I assumed everything goes smooth. The point is that originally I didn't really plan to cover this, this section. So the real definition involves singularities. The way you think about this is that you want to think about the motivation coming from the minimal model program. So Mori fiber spaces are like terminal objects in an MMP for univol varieties. And as such, if you start with the smooth varieties and you run a MMP, you land into something which satisfies some properties. So definition of Mori fiber space allows for singularities, but you require two things. The first thing that you require is that the singularities are terminal. Remember, this means that all the discrepancies are greater than 1. For instance, for surfaces, that's the same thing as smooth, but in high dimension, you run into terminal singularities. And the second thing you require is a condition on the class group. So you ask the variety is Q factorial. So this means that every Veil divisor is Q Cartier. Or if you like, the local rings of the variety are Q factorial. Okay, so we need this condition in order to talk about birational superrigidity. So now the observation here, so the remark here is that so the singularities of X are in codimension at least 4. In fact, I think under my assumption, I could mention at least 6. Sorry, let me just say for a second, at least 5. Okay, there is still the n equal to 5 case that should fall in this theorem, hopefully. No, not quite. So this implies, you can check that this implies that X is in fact is factorial. I mean, this is a subtle point. So these are ordinary double points. Ordinary double points is, I mean, let's look at this way. A cone over a quadric is factorial if the dimension is at least 4. Of course, in 3 dimensions, that the best example something is not factorial, right? But in high dimension, is factorial. But this is analytically. So whereas the condition here is in the Zariski topology. So that's where the statement becomes non-trivial, but it can be checked. This is true. And the other thing is that because we have ordinary double points in dimensional list 3, this implies the singularities are terminal. Okay, so this is just to say that we are in a setting where it makes sense to ask the question by rational rigidity. In fact, also Lefschetz will say that the Picard group is generated by the anticanonical class. So we have exactly the same kind of information we had before. So this is one remark I want to make. The second remark is that because of the singularities, in order to apply Publico's multiplicity bound, we need to cut down with a general hyperplane section to avoid the singular points. So let me comment on this. This theorem of Publikov is a global statement. So it's not about locally, what's happening locally. It's in a projective variety because we use this computation in intersection numbers. The singular point, the proof breaks down at the singular points. The count of multiplicity, there is a difference in the notion of multiplicity of a divisor at a singular point. I have a sign multiplicity of the divisor, and I have also a multiplicity as a number in the power of the maximal ideal of the local equation. Those two numbers are not the same. And in fact, let me give you an example to show you that if I don't remove the singularities by taking a plane class, the Publikov statement is false. Suppose, for instance, I take Q inside P3, quadricon. So it's a quadricon, let me just draw a picture. It's a quadricon over a smooth conic. So it has a vertex point. This is in particular, this is an example of an ordinary double point. Now, suppose I take a line through this coin, and I take now at the tangent plane at a point of the line, any point, doesn't matter, it's all the same tangent plane. So this is just the cone of a tangent line of the conic. So you just take maybe another point Q. This is the line L, and this is the tangent plane Q of the quadric, which is the same as the tangent plane along the line to the quadric. So this tangent plane Q intersect with Q is some divisor D, which by definition is cut out by an equation of degree 1 on the quadric. But D is equal, as a divisor, is equal to twice the line because it's cut out by something that is tangent at every point of the line. So I apply this coefficient 2. So this means that the multiplicity of this divisor D along the line is equal to 2, which is greater than 1. So this shows, if you just look back at what the bound of the Publikov bound on multiplicity of divisor was telling us, it was saying that the multiplicity along the divisor. So another way of saying that, maybe that's the easier statement, is that Publikov, a very special case of Publikov bound on multiplicity is the following statement. If I have a smooth hypersurface in projective space, and I look at a tangent hypersurface, a tangent hyperplane at any point, it's going to be tangent only at finitely many points. Okay, so the restriction is going to be a divisor which is only singular finitely many points. But if you have a singularity, then this example shows that this is no longer true. So this means that we need to be a little careful when we use this Publikov bound, and this we're going to lose something because if I try to bound the dimension of a locus of high multiplicity, in order to do that, I need to cut down first. This means that whatever dimension I have, I'm going to have an extra dimension because I lost that information. Anyway, we're going to see this in a moment. Okay, so now with these comments, we can now move on to the proof of the theorem. So, as in the smooth case, we're going to use an autofile inequalities. Inequality produces us a movable linear system. So we assume that there is a rational map. It's called a contradiction. So there's a movable linear system. H inside minus R kx, which is the same thing as x of R. And if D inside H is a general member, general divisor in the linear system, then the pair x 1 over RD is not canonical. Okay. So what does it mean? It means there exists some divisor G over X, and there is some number. It's convenient to fix this number right now, smaller than R. Think about the canonical threshold, which I did not define, such that the law discrepancy along G of the pair is less than 1. Actually, I now use C for the coefficient. I can scale it down a little bit and maintain the statement and be less or equal than 1. Okay, so what I'm going to do is going to let T be the center of G inside X. So this is a subvariety inside X. And I'm going to fix P inside T be a general point. So this is my hypersurface X. And I have a center T, which I don't know if it's zero-dimensional or polydimensional. But then I'm going to pick up some general point P. Okay. And I know that the pair is not canonical along the center. In particular, it will not be canonical P. So now I use the public of bounds. Again, first I need to cut down to remove all the singularities, cut down to general hyperplane section, and then apply public of bound, and then whatever conditional dimension, just add 1 to it. And what you see is that if D is inside H is a general, then the set of points inside X with the multiplicity of X of D is greater than R. That's the set of the dimension of the set. Before we said this dimension was 0, but in fact now we cannot say that. The only thing we can say is at most 1. And now if I have 2 of them, general, and I take Z to be the intersection, the complete intersection, and I can look at the dimension of the set in X, so that X of Z is greater than R squared, less or equal and 2 again. So the unit, this estimate of the dimensions are off by 1 because of the singularities. Okay, so notice that the first bound on dimension implies the dimension of T is at most 1, because I know that the T is contained in this set. That's something we argued before as well. Before, on a smooth case, we were able to conclude that T was 0-dimensional, so just a point. But now we don't have that. We have T could be dimension 1. Okay, so now a couple remarks. So if the dimension of T is equal to 1, then we can pick P in T to be a smooth point. A smooth point of X. However, if the dimension of T is equal to 0, then P may be a singular point. And there's nothing we can do about that. So either one or the other. We either lose on the dimension side, or we lose the fact that we are on a singular point. And the loss in either case is kind of the same. Okay. So now what we're going to do is that what we did on the smooth variety, we cut down with an hyperplane section through P, and we went from something which was not canonical into something which was not log canonical, going to the log canonical threshold, and then move on from there. Right. Now, in order to get to something which is not log canonical, because T might be of dimension 1, I'm going to have to cut down twice. So I'm going to take Y now to be an intersection. They call it V intersect V prime inside X containing a point P. So is take to be the complete intersection of two hyperplane sections. I mean, I should say general. V and V prime on X passing through the point P. So I need to cut it down twice. So what you see is that Y, what is Y? Y contains a point P. It could be a singular point. It could be an ordinary double point in Y. And now Y, because I cut down dimension twice, is the degree the same, still degree n. And now it lives inside a Pn minus 2. Another thing I see is that by cutting down twice, so we had this set here, it was almost two-dimensional, but because I cut down twice, I cut down the set to a finite set. So we see that the set of Y is inside Y such that the multiplicity of Z is at least 2. It's finite. It's a finite set. Okay, so what do we gain by cutting down twice? So by cutting down twice, we get a pair Y, C. Now I pass to Z. That is not KLT at the point P. So let me maybe explain this in a moment. So one time ensures, sorry, we cut down one time to ensure that the canonical, just put in quote, canonical center, this T that is started from, becomes 0-dimensional. And then one time to apply once we get down to something which is like the singularity is zero-dimensional, then we can apply inversion of adjunction. So if T was already zero-dimensional, then the first time you cut down, you can already apply inversion of adjunction. But if T is one-dimensional, you first need to cut down something dimension 0, and then you can get the inversion of adjunction. Okay. So, and now we follow the same strategy. So we double before, now we double the boundary. So, and we look at the multiplier ideal on Y of 2C 0 to Y. And using the multiplicity bound written there, the fact that there was a finite set of bad multiplicities, then we show that this one defines a zero-dimensional scheme, sigma inside Y. Okay. And the same computation on law discrepancies, it shows that the log canonical threshold, this Y of this sigma, is less or greater than 1, which means that the pair Y sigma is not KLT. So it's not just a non-zero scheme, but in fact it's very singular. So what we did last time is that we apply an idle vanishing, and we can do this again. So with idle vanishing, we say what? We said if I look at H1 on Y of omega Y twisted by 2, I'm going to write it in this way. The cohomology vanishes. So let me explain this again. I look at the multiplier ideal. I look at the equation cutting out this scheme, this Q scheme, and the degree of this equation is at most 2, because C is less than R, and the degree of the equation cutting out Z, degree R. So this 2 is to compensate the degree of the equation cutting here, but then I need to also introduce the canonical class. So that's what this omega Y does. So because, and here's the difference from what we did last time. Last time we only cut down once, so omega Y was trivial. And now because we cut down twice, this become actually general type. So omega Y is actually O1. So this thing together is actually, oh, is a Y by the way, is OY of 3. So this means that there's another place where actually we lose a little bit, and that's cause a difference in the result of the bounds on M. Okay, so and now you apply the same argument. So if the H1 vanishes, then I have a surjection from the section of this line bound OY of 3 to the section rings of sigma, and this implies that H naught of the section ring of sigma is at most the dimension of Y of 3. The space of section of Y of 3. That's the same as the one we compute on the projective space. So, and this turns out to be N plus 1, 2, 3. Okay. So now we look for a lower bound. So you cannot apply the lemma on the length. Remember, we did this computation of what would maybe I should state what the lemma was. Let me stay the same. So suppose R is a regular local ring, and I have an idea of A, and the length of Arman A was, let's say, dimension n. There was 2 to the n plus n just 2 times 3 to the n minus 2. So, but there is an important assumption here, which is the fact that we require the ring to be regular. I mean, that was part of the computation. We start counting lattice points and monomials. So we use these local parameters on R. So, but here now, I don't know that Y is regular at the point P. So the way you do that is I take a degeneration as follows. So to apply this, if our P inside Y is an ordinary double point, so it's not regular, what you're going to do is I take a degeneration. So think about the degeneration to the normal cone. In this case, we have degeneration to a tangent cone. So that's something you can do using just rescaling the variables and taking some limit. But now what I'm going to do is once you take it to tangent cone, that's a smooth quadric. And then what I'm going to do is I'm going to degenerate further just to degenerate the smooth quadric into a union of two planes. So the way you do this is that you fix a sister action on the coordinates. On the first two coordinates, the sister action act with weight 1. And then on the other coordinates, maybe I put weight 2. So when you do this, you see that under this action, Y will degenerate. Suppose that Y is defined by some equation. H is going to be the sum from I goes from 1 to n minus 2, I guess, xi squared plus I other terms. You do this degeneration, this end up just picking up the initial terms in this monomial, in this semi-order with respect to these weights, which is precisely the union of two planes. Because the equation will degenerate to the equation x1 squared plus x2 squared, which is defines two planes. Okay, see, under this degeneration, I also have this close-up scheme sigma, and that will also have a flat degeneration. To some sigma prime. Okay. Okay, so this is flat. So I do this locally. On some affine chart. Okay, so, and now I use a little bit of adjunction, inversion of adjunction. So remember we have this assumption on local Nichols ratio of Y sigma being less or equal than 1. So so this is the same thing as saying that minimal low discrepancies at the point P, because this is acting at P, of Y sigma is less or equal than 0. Now, using inversion of adjunction, that's the same as the minimal low discrepancy on the ambient space of sigma plus Y be less or equal than 0. Okay, but now we do this degeneration and we use semi-continuity, or in this case, we just semi-continuity of local unequal thresholds to see that when I take the degeneration, I end up to something I can write in this form. Okay, so the scheme sigma degenerate to sigma prime, and this hypersurface y degenerate in the union of two planes. So I'm going to write it this way. And now we're going to apply inversion of adjunction in the other direction and start restricting. So I restrict maybe to the first one. So I take sigma prime and I restrict it to the first one. I just going to sigma prime 1. And then I restrict the other guy to the first one. So I'm going to H1, 2, the intersection of two planes. And I use inversion of adjunction one more time to land in the intersection of two planes. And I restrict sigma to that. So now I'm finally in a situation in which I can estimate my, so this is an a to the n minus 4. So now the lemma implies that the length of all sigma prime 1, 2 is at least 2 to the n minus 4. So I pay a price because I cut down the dimension a lot of times, but still I get a bound that goes very fast. Okay, so of course, for this computation, you need to assume something about n being at least 6. But now remember that under this process, because I'm restricting Z and then I come from a further generation which preserve lengths anyway, I have a bound like this. So now I have a lower bound on this length. I had an upper bound from Nadal vanishing. So you compare the bounds on this length. We get a contradiction as soon as n is greater than 9. So this proves the theorem for n greater than 9. And in the last 10 minutes, let me discuss quickly the remaining cases. So there are remaining cases. Maybe before I do that, any questions about this? So you see how the singularity exists, the presence of a singularity affects the proof in several steps. And every time we lose a little bit. Yes? Flaminio, do you have a question?
No, I was saying yes, okay.
Okay.
So the times you have to cut down, no?
Yeah. So this double point also requires, first of all, we have to lose one dimension because of applying this public of bounds. So we lose one dimension there, and now we lose one dimension here to apply this lemma. We get a kind of somewhat weaker bound. But still we get a bound strong enough to cover most of the cases.
Yes.
So there are some remaining cases, which are when n goes between 6 and 8. And for this, we can deal with these projections. So let me just discuss the case n equal to 6, just to make it more concrete. The discussion is very similar in all the cases. And also, I'm going to do assume for simplicity P inside Y is a smooth point. P singular, need to use this matter of discrepancy and cut one more time. because of the difference between discrepancy and matter discrepancies. So I'm gonna not do that. The idea of the proof is very similar, just an additional little complication to take care of. But let me just do the simplest possible case when P is a smooth point, just to give us an idea of how you conclude using these projections. So what you do is you have Y is the degree 6, and now Y lives in some projective space of dimension 4. So you're gonna take a linear projection to P2, so some general linear projection. And now I have a map. Well, so this is really, there is a little bit of indeterminacy here, but it's defined, it's well defined at the point P. So again, if you like, you can just blow up the center of projection and reduce to a well-defined automorphism. You can do that. Okay, so instead here, remember that we have this scheme, 0, 0 to Y, which is a codimension 2. Y is the dimension 3, and I go from dimension 3 to dimension 2. So Z is a dimension is dimension 2. Sorry, is dimension 1. So in P2 will be becomes a divisor. So instead here, I'm gonna look at delta. Or maybe I don't want to write because I put the coefficient already. Like this. I'm gonna take delta to be the following. I rescale it by the coefficient coming from the theorem on projections. Okay. So the fact is that the log canonical threshold Y was 0 set to Y was less or equal than C. So this implies that the log canonical threshold of this pair, so maybe just write it this way. It's not KLT, okay? This is by the theorem projection. Okay, however, multiplicity bounds imply that if I look at the multiplier ideal of this pair, it defines a zero-dimensional scheme, W inside P2. Okay, again, you just make sure that the multiplicity of this divisor of these reducible components is less than 1, and that's what you need to control. Okay. Now, the degree of delta, what is it? Let me actually do this computation. So this is C squared divided by 4 times the degree of Z related to Y, which is 6, which is the degree of Y, times R squared. But you remember that C was smaller than 1 over R. So this is less than 3/2, which in particular is less than 2. Okay, so now to conclude, I'm gonna use this net dimension again. And conclude by the same argument. So let me just write it out and then we're done. So I see that on P2, I need the degree 2 equation, But then remember that we also have the canonical class, and now the canonical class on P2 is very negative, which is to our advantage. So this would be 2 minus 3, so it's minus 1. Okay, so this multiply radio is equal to 0. So we get a surjection. Again, let me just do this one more time here. 2 minus 1 to H0 of OP2 minus 1 restricted to W. But that's 0-dimensional, so it doesn't really matter. The twist is just this guy. So this guy is different from 0, and this y is equal to 0. So you get a contradiction. Okay, so any questions on this? So it's again the same argument, and in fact, in this situation, it's actually even easier. I'm not really estimating dimensions and try to get computing dimension in 2 different ways. I just get a contradiction directly as an empty vector space subjecting onto a non-empty vector space. It's clearly impossible.
And the same occurs also in P7 and P8. Sorry, for n equals 7 and n equals 8. You project.
Yeah, I mean, it's the same. It's essentially the same computation. You need to be a little careful about. I'm not giving all the details here, because, for instance, this assertion that this thing defines a 0-dimensional scheme, it requires looking at these things a little carefully. When you do these projections, you want to make sure that the multiplicity don't increase. So for instance, you want to make sure you want to estimate the dimension of the secant variety and the tri-secant varieties and sort of things. So there is a little bit of computation going there. When you go in dimension, when n is equal to 8, in fact, I cannot conclude it's 0-dimensional, it's only 1-dimensional, so I need to cut down one more time, for instance. And then if P is an ordinary double point, I know that the pair is not KLT, but I don't know about the matter law discrepancy, so I need to take care of that. There is a difference, but I know how to compute the difference because we have a formula for that with the Jacobian ideal, which for an ordinary double point is just a maximal ideal. So at the end of the day, I just need to cut down one more time to do that case, but because there was 0-dimensional in the first place, it was easier. There's still room to do that.
Okay, thank you.
So yeah, so this is the end of the proof. I mean, or the sketch of the proof. Are there any more questions about this proof in particular, or birational rigidity in general? So what I'm going to do next time is that in the last 2 lectures, I'm going to change topic. This time I'm going to do it. And I'm going to talk about rationality in families. So how does rationality behave in families? So this is going to be a completely new topic. Okay, so stop recording.